Day 10. Let's build a basic neural network from scratch in Python using only NumPy to demonstrate how a neural network works under the hood. We'll implement a simple feed-forward neural network with one hidden layer and use the sigmoid activation function and mean square error as the loss function. So let's get started. So first, let's go ahead and create a new file. I'll call it as day10.py. Now here, first thing that I need, as I mentioned, is I need to import NumPy. So I'm going to say add the comments, import, increase the size, necessary libraries. Since we said that we are just going to use NumPy, which is used for matrix operation and mathematical function, we'll import that. Import NumPy as NP. Okay, next thing that we want to do is we want to write the sigmoid activation function and its derivatives. So I am going to say sigmoid activation function and its derivative. For that, I will write a function def sigmoid, pass it x as the parameter, and return in this case 1 divided by 1 plus np dot exponential of minus x. That's our sigmoid function. And now let's do the sigmoid underscore derivative. Now derivatives, if you learned in school, good. If not, the way to do it is I'll say return x times 1 minus x. So that will give me the sigmoid derivative. So these are the two different ones. Next thing that I want to do is get the mean square error for loss function. So for that, I'll say mean squared error, or also called as MSE, loss function. Now to define this, I'll say define mean underscore squared underscore error. It takes two parameters, y underscore true and y underscore spread, and this will return back to us the numpy dot mean, and I can say np, so mean square error, so I say square here y underscore true minus y underscore spread. So what it does is it calculates the mean square error between the true and the predicted output. This is the loss function used to measure the performance of the model. Now once that is done, we are going to go next, do the basic neural network class here. So this class we will define by saying class basic neural network. Perfect. And the implementation for this is, first let's write the initializer. Now initializer, we need to pass four items, which is the object itself, input size, hidden size, and output size, which initializes the neural network with random weights and biases. So I will say def underscore underscore initializer. Now this is how we do initializer in Python classes. Self, I'll say that I need input size, not shape. I need the hidden size. I need the output size. And this takes in self dot weights underscore input underscore hidden. So this is one of the variable which I'll have to set from np dot, I'll use a random dot RANDN and pass it the input size that I have, and I'll pass the hidden size that I have. So what this does is this weights input hidden is actually the weights between the input layer and the hidden layer. So that's what I am doing here. Next, I want to get the weights self dot weights in or hidden output. Okay, I'll probably do it manually. Hidden output. Make sure I don't do any typos. Output is equal to, now this hidden output is the weights between the hidden layer and the output layer. So I'll have to say np dot random dot randn and pass it the two things, which is the hidden size I mentioned and the output size. So I'll pass that to this. Next is the bias hidden. So self dot bias underscore hidden. Now this is the bias for the hidden layer. So to do that, I will say np dot random dot randn and pass it 1 comma hidden size. And next I need self dot bias output. Now this is the bias for the output layer. So similar to the above, just copy this here and just change this to output size. So this will give me the bias for the output size. Now next step is to write the forward pass. So inside this function, inside this class itself, I am going to say forward pass. Now to create the forward pass function, you'll probably define first forward, and it takes two parameters. One is the self object and next is x, which is the features. So I can say self dot hidden. So in this case I need the hidden output, hidden underscore output, sorry, hidden underscore input, not output, hidden underscore input, which will be np dot dot, and the function takes in x, it takes in self dot weights of input hidden, so I'll pass that, and plus self dot bias hidden. That's what it takes. So this will make sure that everything is perfect. So this will give me the first hidden input. Now that's for the hidden layer calculations. We have input to the hidden layer, which is using np dot dot, and then we'll have the output from the hidden layer. Now the output from the hidden layer, like before even doing that, let's complete the hidden output. Hidden underscore output equal to, I'll call the sigmoid and pass it self dot hidden input. And next, now for the output underscore input equal to np dot dot function, and to this I'll pass self dot hidden output, and next is self dot weights hidden output, and plus self dot it needs the bias output, so that I'll pass. Perfect. So once that is good, the next thing that we need is pass the self output. So I'm going to say self dot output equal to sigmoid self dot output input, and then I'll return back here self dot output. I know there's a lot of input output, so be very careful what you type or what you're looking for. Understanding this is much easier when you write the right things. So now finally we'll do the next thing that we want to do is the backward pass and the weights update. So to do that, first I'll write the function for that. I'll say backward pass and weights update. So to write this function, I'll say def backward, keep it simple, and this takes bunch of inputs, which are a bunch of parameters. Is self, it needs x, it needs our target, it needs output, and it needs something called as learning rate. So since this backward function performs the backward step, first we will need to set up the output error. So output underscore error equal to, so this is output error is the difference between the actual output and the predicted output. So actual output minus the predicted output. So that's how you define it. Next we have is output underscore delta, which is the adjustments for the output layer based on the error and the derivative of the sigmoid function. So to do that, I'll say output underscore error times sigmoid derivative of the output. Perfect. Now next thing that I need is the hidden error, or hidden underscore error. This is the error for the hidden layer propagated from the output layer. To do that, I will say np dot function, and it needs output underscore delta. It needs self dot weights hidden output dot t. So this will give me the hidden error. Next, I need the hidden delta. Now hidden delta is the adjustments for the hidden layer. So now to do that, I'll have to first get the hidden underscore error, there you go, times sigmoid derivative of self dot hidden output. That will give me the hidden delta. Now next, I need to get the weights and biases update, which are gradients. The gradients are used to update the weights and biases using gradient descent. So to do that, I will first get the self dot weights hidden output equal to or plus equal to, based on whatever the value is there before, I will say np dot and pass it self dot hidden output dot t, comma, I'll have to pass the output delta to it, so output delta times learning rate. Okay, so that will give me update the self weights hidden output. Next, I need to update the self dot bias bias output. Now this I can increment by saying np dot sum, and the parameter that it needs is first is output delta. Next it needs an axis, I'll say 0, and it needs keep dims equal to true. I'll set that to true, times learning rate. Next I need the self dot weights input hidden, self dot weights input hidden plus equal to np dot, and inside this function I'll pass x dot t. I need hidden delta and multiply this finally by learning rate. So next, finally, we need the self dot bias hidden. For this, I will have to increment n by np dot sum, pass it hidden delta. I need to pass axis of 0, and I need to say keep dims equal to true and multiply that by learning rate. Perfect. So this will give me my backward pass and weights update. Next thing that I need to do is train the neural network. Now to train the neural network, I'm going to go here and say train the neural network, and I will move it up and say def train, and the parameters that I'll pass is self x comma y comma how many epochs I want to train it for, and I will pass the learning rate. So to this, first thing now I have to do is run through a loop. So now this trains the neural network for a specified number of epochs. So I will first say for each epoch in range of epochs, I will run this. First I need the forward pass. So I need to perform the forward pass here. Now to perform the forward pass, it's very easy. I'll just say output equal to self dot forward. We've created that function and it needs one parameter, which is the features, and that's what I'll call x. Next, I need to create the backward pass. So I'm going to say self dot backward, and to this I'll pass all the parameters x comma y. I need output, I need the learning rate. So this will do. So first we'll perform the forward pass, the next one performs the backward pass to update the weights and biases, and finally we'll have to do the loss calculation, which is every 100 epochs the loss is printed to track the model's progress. So we can do that here. I can say if epoch mod 100, so every 100 epochs equal to 0, every time it hits 100 I will say loss equal to mean squared error by underscore output, and then let's print it out here. F epoch, which epoch it is, since it's every 100, so we know which one it is, every 100th one. It will print this, and loss equal to, you can print the loss here, loss. This is perfect. So I have that, everything is perfect. Now next thing that I need to do is training with the XOR data set. So to do that, let's do that all the way outside. Let's go outside and let's create a XOR data set. This is used to test the neural networks usually. So I'm going to say x equal to np dot array. I'm going to create an array or a list of items with, let's say, 0 comma 0 first item inside this. I'll say 0 comma 1 next item. I'll give another 1 comma 0, and next one I'll say 1 comma 1. So my XOR fields, this is the input data. Now y, which is my target, I'll say np dot array, and this will have the expected output, which is the XOR value. So I am going to say 0 and 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is again 1, and 1 XOR 1 is 0. So these are the output from the above calculation. Let me make sure that I keep it consistent. So this is the expected output. Now next step is to create a neural network instance with 2 input neurons, 2 hidden neurons, and 1 output neuron. So to do that, I'll say nn equal to basic, call that neural network that we created, and I'll say input size, I'll say, as I mentioned, 2 input neurons, hidden size, I said 2 hidden neurons, and output size I want is 1. So I need 1 neuron as output. Now let's go ahead and train the neural network here. I can say nn dot train, call the train function on it, x comma y, which is our XOR data set here. Give it a epochs of, let's give it a something big, I'll say 10,000. That should work. Learning rate equal to 0.1. That's good. Now let's test the neural network with the XOR data set. So let's print it out. I'm going to print /n, next line. I'll say testing the trained neural network, and next I'll say for each of the items, I'll say for I in range of, let's say, length of our input, which is length of x, I want to say print f, and I'll say input is x of I, then comma, then next I need the predicted output, and since I've trained it so many times just for a simple XOR operation, it should work, but you never know. Forward x of I is the predicted output, and I want to also see what the actual output is. Y of I. So that's my actual output from here. So this looks good to me right now, and we can go ahead and run it. So what we have done here is we have initialized. So once we call this function here, we initialize the neural network using the initializer here with random weights and biases. Then we did the forward pass, where the input is passed through the network to produce an output. We also did the backward pass, where the error is propagated back through the network and the weights and biases are updated using the gradient descent. And we did training here, where the neural network is trained over multiple epochs to minimize the loss. Finally, to test, after training, the network's performance is evaluated by comparing comparing predicted and actual outputs. So let's run it and see how it looks like. I'm gonna say ls, and this is my python day 10.py, and there you go. So every 100, 0, 100 epoch, it gave me the loss that is there happening. Since it's 10,000, it stopped at 9900 as the last printed output. Tested neural output, let's say 0, 0, it says 0.04, very close to 0. This is 0, 1, it says 0.94, very close to 1. And this one 1, 0, 0.9, which is very close to 1. And again 1, 1 is 0.0, which is very close to 0. So it did a pretty good job. I would say 99% good on the prediction. So there you go. We have created our own basic neural network from scratch. So try it out. Let me know if it works. And if you have any questions, let me know.